Welcome to week 6 of University of Delaware Geography 473, 673. This week we are covering remote data extraction. We're going to be talking about two different services today called THREDDS and ERDDAP. And both of these are just different pieces of software that allow us to share data and host them in public repositories. So what is ERDDAP? This is an ERDDAP that I help manage, and what it is a quick and easy way to visualize and distribute data. So for example, we've used GOES SST, or GOES Sea Surface Temperature, here today, or in this course, and basically this is where I originally got the data from. So you have a nice little visualization. You can kind of go through all these different times. You can play with the data. You can shrink your latitude, shrink your longitude, and really just try and visualize the data. You can bring it back in time. And this is a lot of different things you can do here. But you can also pull out the data yourself. So there's a data access form. You can actually download a multitude of data through that, or you can actually just come here and you can download the data or this image. And so you can actually come into this file type. You can download it as a netcdf file, just this little piece of data. So this is ERDDAP. It's very nice. It's very user-friendly. And then there's THREDDS. And THREDDS, this is a THREDDS that I help manage, and it's just a little bit more computer-friendly. So it's a little bit that it's very easy and quick. You can get data from it very quickly. So that's methods. And the primary method that we are going to be concerned with is OpenDAP. And this allows us to talk directly through THREDDS. So this is a really nice feature. THREDDS and specifically OpenDAP are awesome. There's other ways. These other methods also work, but they're a little bit more for pointing and clicking. What we're going to talk about today is with remote data extraction, we won't need to point and click at all. All we need is to have the appropriate links, and we will be able to query the data that we want and need straight from R without ever leaving it. So let's go ahead and let's open up week 6 data extraction. And as we kind of talked about, we have a lot of different looking things so far between ERDDAP and THREDDS, and we've downloaded data either individually, or hopefully by now you've downloaded a multitude. But the thing about downloading those pieces of data is they're really useful. It's really useful to have if you're just working with like a specific data set or just, a small data set. But if you're really working with something where you require thousands of files or processing through thousands of files and you don't have them locally, or let's say you need 1,000 files, you don't have the room to save it on your computer, and you're only really concerned about a small portion of that file. So for example, if you have a data set covering the entire world and you're only concerned about data over Delaware, then you don't need all that data. It's just so much of it's just going to be wasteful to you. It's going to take up and hog space. With THREDDS and ERDDAP, you can remotely extract just that piece of data that you want. And that is the advantage. So we talked about THREDDS. This is the computer-friendly one. So there's a number of different NASA, NOAA, University of Delaware THREDDS. There's also University of Massachusetts has one. So we manage a few here at University of Delaware. We already showed you one, but then there's also the Jet Propulsion Laboratory and Oak Ridge National Lab, Pacific Islands and Ocean Observing System. So there's a ton out there. They all house so much data. So we're going to be using the University of Delaware Satellite Receiving Station THREDDS, which we already kind of took a look at. And we're mostly going to be concerned with GOES R. So really what we really want to take a look at here is we're only really going to be concerned here with GOES JPL SST. So this has been updated, and now we're going to be using GOES JPL SST. So I mentioned we use OpenDAP, and what that means is we can get a link to the netcdf database. So I'm going to copy that link over. And this is going to be really important here. And what we're going to do, this is the link that I just copied, and we're going to use NC Open on that file directly. So we're directly linking this to OpenDAP. So I printed that out. Here's what it looks like. So we have directly gone, so these are the different variables within this entire data set. And then take a look at the dimensions. We have 1,800 latitude values, 2,500 longitude, 26,469 different time slices. In other words, we have 26,469 files, period. So we have a ton of data here, and that is what makes us so easy. So we have opened up a channel that we can select data with right here. It's called Goes NC. So you can actually print out, so this is kind of a clunky way to view all of these different, it's useful, but it's kind of clunky because you kind of have to really look in here. We have a projection string with an EPSG code, that's great. Then we have sea surface temperature, the dimensions are longitude, latitude, time. It has a long name, sea surface, subskin temperature, a standard name, comment, and units and stuff. But we can also just use names. And so Goes NC that we have, even though it's just this kind of ambiguous, like large data channel, it still has information regarding this particular data set. So we have file names, IDs, groups, DIMs, and var. So if we just print out the var and then we only want the names, we have projections, sea surface temperature, quality level, analysis, zenith angle, bias, and so on and so forth. So how is the time stored? Print out, we go to the dimensions now. We know that time is a dimension, so we have goes NC, $dim, $time, $units. The units are seconds since 1970-01-01. Now, this is also known as epoch time. And this is really, it's kind of shorthand for the inception of computation. So that is what epoch time is. It's just kind of a gold standard starting point for data set time. And so we're working in seconds since this time. And this is a reference point. So basically what we have here is our data set is stored with time, but instead of it just saying, you know, January 15th, 2021, it is the seconds between January 5th, 2021 and 1970, January 1st. We're going to work on backtracking everything out. So let's print out the length of Goes NC time vals, just 26,469. And now what we're going to do is we're going to use that last val, that index, and we're going to extract the epoch val. So this is our total number of seconds between the last file in the database and 1970, January 1st. Now we can convert this to human time. So instead of it being in seconds since, computers really love seconds since. It's kind of nice. It's just one numeric, one number right here. That's nice. There's no commas or anything. But we can actually convert this using ASPOSIX CT. You can convert it to human time. And 2021, 128. So January 28th at 12 Eastern Standard Time is the last file that has dropped. There's also a function called anytime from this sweet package called anytime. We can type anytime epoch val, and it will automatically convert that epoch val to a human time for us without the ASPOSIX CT, and the added origin automatically assumes that the origin is 1970-01-01. So at this point, what we're going to need to do here is we are going to want to convert this over. So let's say, for example, that we want to extract data between July 14th, 2019 and July 16th, 2019. Remember, all of our time values are stored in seconds since 1970. So the way that we're going to need to do this is we're going to need to convert our human time to epoch time. We can do that using as numeric of an as POSIX CT. So basically we have this start time, right? What's the class of it? It's just a character. That's not good. We need a date. We need to have a date class. So that's what we use as POSIX CT of start time. And the format is going to be year, 4-digit year, dash, 2-digit month, dash, 2-digit day. This little format string right here is telling the computer to format our date string is year dash month dash day. So this needs to match the format of this character string. And this is a time format. This is kind of synonymous across all programming languages, no matter what you do. Dollar or percentage sign capital Y indicates you have a 4-digit year. Then we have a dash, right? Then we have percentage sign lowercase m is 2-digit month. Then we have another dash. Then we have percentage sign lowercase d is 2-digit day. So now, if I run just this little as POSIX CT, now we actually have 7/14/2019 Eastern Daylight Time. And if I run a class on that string, it's a POSIX CT class. That's awesome. And now we can convert it to an epoch time using as numeric. So my epoch start time now is going to be this long number. So same thing goes for the end time. If we have 7/16 as our end time, that's great. So epoch end time is that. Now, we have the time values converted, but we need to find the index. So we need to find where these epoch start times and the epoch end times are located within the data set. We can do that. So remember, if I print out goes.nc dim time vals, and if I just print out 1 to 10, remember this is 26,000 files long. We have 26,000 different timestamps. We want to find what is closest, the data file that's closest to my epoch start time and my epoch end times. So the way that we can do that is using which min and absolute. So we're finding which value is the minimum difference. So we want to subtract all of our values from the epoch start time, take the absolute values so that we're working in, all in positives, and then we're going to find the minimum difference, and that'll be the closest file to our start time. So, and we're returning the index, right? So the index of July 14th, 2019 is the 13,384th file. And let's just print out, we'll use this index 13,384 in the vals to print out the associated epoch time. And look at that. It's the exact same as our epoch start time, the exact same. So we found a perfect match. That's awesome. We're going to do the same thing here for end time in a bit. So we have our start time, but what do we do about the longitudes and the latitudes? So let's say, for example, that we selected a time window that we want to view the data through. Let's also suggest that we want a latitude and a longitude bounding box that we want to center the data over. So these are huge files. They cover the Northwest Atlantic. Let's just say that we only are concerned with data in and around the Delaware Bay. So we're really focusing our window here, and the way that we can do that is going to be a similar way to the time, only now we're going to be working in latitudes and longitudes. So let's just print out ahead of the long vals. So this is what it looks like. It's -99 and decreasing. So we go, the 100th value, the 100th index value of the longitude vals is -98.01 degrees west. So what this means is the 100th lon value is that, and so an index of 100 returns that. So basically, if we have a set bounding box of -77, -73, 36, 42, so this is our box, these are the corners of our bounding box, we're concerned with the west longitude of -77, so we want to find the closest index value of that. And the closest index is 1151. So now, if we go goes.nc dim longitude vals, and we return the 1151, it's -76.99. Not too far off from -77. So let's do the same thing for the other corners of our bounding box. We still have an east lon of -73. We have a north lat of 42 and a south lat of 36. So everything is indexed, and now what we get into is the count. So why are we covering this? When we actually come down here and we want to extract the variable for our specific time window and specific geographic latitude and longitude box, we are going to need to provide the file this is coming from, or the channel that directs us to that link, the variable we want to pool the data for, which is sea surface temperature. We need the start. So in other words, we need the corner, one corner of the data set, the lowest corner, and we need to, that's where we're going to start counting from, and we need this, the start time that we can start counting from. And then we need to know how long to count, how many values, how many longitude values are we going to count before we get to our east lon, how many latitude values are we going to count until we get to the end, and how many time values are we going to have to count until we get to index end time. I really wish that they had another function that would just how you'd have start and end instead of count, but we kind of have to do this backwards thing where we have to do end minus start and to find our count values. So that's just kind of how this is working. So a little bit wonky, but it all makes sense. So we have a time count, which is just going to be the difference between end time and start time, and it is 48. So that is the index, that is how many different indices exist between the start time and the end time. Why does this make sense? We wanted 2 days of data, and the data comes in hourly. So the difference between our start time and our end time is 48 hours. So that makes sense that we have a difference of 48 indices. As for lat and lon, we have a lat count and a lon count. It's just going to be the absolute value difference between north lat, south lat, index, and these are the indices, by the way, right? So it's the indice difference. So we have a 300 difference there and a 200 difference there, and these are going to be our counts. So that's awesome. So now we need to talk about the start. So, typically, if we were just looking at this, we were looking at a file of sea surface temperature, we would want to start it at the lower left-hand corner, right? We would want to count from -77 all the way to the right to -73 for longitude, and then we'd want to count from 36 all the way up to 42 for our latitude. We want to count the box. However, because this is a netcdf file, sometimes in the concern of space and storage, these files can be stored flipped upside down. We've experienced this way back in raster visualization and reprojecting and writing rasters, where we had to transpose and we had to flip this raster, this netcdf file that we read in. It's just an artifact of the file storage. It just stores it more efficiently. Why does this matter? Because look at our indices here. If we print out our index of our north lat and the index of our south lat, the index of our south lat is higher. Even though our south latitude is 36 degrees, we should typically count up to 42. We need to count up from north lat to get to south lat. This is because it's flipped upside down. The data is stored upside down. The latitudes are flipped. So as a result, when we come down here and we use NC_var_get to grab our SST.c, our start is our north latitude. Now remember, the indices, if we print this out again, goes that NC, and we come up here, we find sea surface temperature. The data is stored longitude, latitude, time. Longitude, latitude, time. And now we have to start from our north latitude, and we need to count using the lat count to get to our southern latitude. So we're counting from 42 degrees to 36 degrees using indices and counts. The longitudes and time are normal. They're intuitive because we're counting from our west longitude to our east longitude. That makes sense because we're counting up. Our values are increasing from -99 to -90, or sorry, for in this case, -77 and -73. The start time also is intuitive because we are starting from July 14th and we are counting to July 16th. So we add our file, or our channel where this is coming from. This is our link to the database. This is the variable we want to grab from the database. This is when we want to start counting from the database. And this is how long to count from the database. Run that. And there we go. So now let's look at what STC. Okay, so this is kind of wonky right now. Kind of looks unorganized, but basically here's what it is. It's longitude, latitude, and a bunch of slices. So basically you have a two-dimensional grid, latitude, longitude. We have different slices of that grid, and those are the times. So if we print out dim, SSTC, our dimensions are 200 by 300 by 48. In other words, longitude, latitude, time. And now what we can do is we can treat this netcdf file as a raster. So let's load in our raster package, we'll load in our map tools, our raster viz. Now this is the interesting part, right? So let's say we wanted to grab the fourth time slice from our SSTC. So we want all the longitudes, all the latitudes, and we want to grab the fourth. So let's run that line. Now we don't have these other slices, we just have a large matrix called array.sst or r.sst, and the dimensions are now 200 by 300 by 1. We just have one time slice, and that is the fourth time slice. So you can use whatever one you want as long as it's within the first or 48, because you only have 48 different slices. So first things first, we're in Kelvin here. Let's go ahead and let's convert any values that are below 273 Kelvin or 0 degrees Celsius to Na. Why? Because the water would be frozen. So just a little quality control. Now let's convert this to a raster. So we're going to rasterize this array, and let's print out some of that data. Here we go. We have dimensions, 200 by 300. We have a resolution. We have extents. It's just, we still need to add our actual extents. We don't have our actual longitude and latitude values. It has no coordinate reference system. It just has values, and it's stored as a raster now. So we're going to need to add some things. Let's load in ggplot2 before we plot. And then what we're going to do, this is the key thing right here. We're going to need to transpose the data set. Why? Because it comes in flipped inside out. That's just the way that it reads it in, and we just kind of have to adapt to make it work within R. just the nature of netcdf files. They're incredibly efficient, but the way that R reads the way that these packages read in the netcdf files can be a little bit cumbersome. So we need to transpose test SST. Then we're going to get the projection from our channel. Here's our proj string right there. That's going to be our SST CRS. We're going to add our extent, which is our west lon, east lon, south lat, north lat. Give that to test SST. Then give it the proj4 string for the CRS of test SST. Now, when we print out our raster, we actually have a nice coordinate reference system. We have values that cover our extents, our bounding box. And now we can plot. So remember, ggplot2 takes things in as a data frame, so we need to convert our raster with all this information to a data frame. The xy is true, it's kind of a map. So, and then we can just add that into ggplot like we've already covered. Oh, I didn't run this up here. It'll load in ggplot. And there we go. Here we go, sea surface temperature for the 4th time slice of our data set over the Delaware Bay. So that's how THREDDS works. It's a little bit cumbersome, but it's so easy. I mean, we didn't have to point and click at all. And once you get the hang of it, this is so much easier than actually trying to download. And I mean, well, this was for 2 days of data, so 48 files. Imagine if you had a week, so you were dealing with hundreds of files at that point. So it really accelerates the way you can mine data, way you can extract data and perform analysis on that. THREDDS is awesome. The next thing that we're going to cover as far as open data goes is called ERDDAP. So ERDDAP is just THREDDS' sister basically, and it's a little bit more human friendly. It's more for visualizing the data very quickly and taking a look at what's going on before you download. There's a number of different ERDDAP sites that I use that are really useful. For example, Coastwatch and Upwell by NOAA. I mean, there's over like 10,000 different data sets in there. There's so many data sets, it's crazy. So if we wanted to take a look at these different variables like we kind of took a look at earlier, just want to go to the link provided, which is based in the ERDDAP. We're going to come down here to JPL, goes RSST, hit graph. And I should probably start from the very beginning. So this is what it looks like when you just load ERDDAP up and you want to say, I want to view a list of all 49 data sets. Now here's the list of all the data sets, and then you have the graph feature over here. You have the data feature if you just were interested in the raw data. We can just click graph, and there we go. So our last file to drop was 128/1700. So let's use R to talk to ERDDAP instead of us talking to ERDDAP with our mouse. So the first thing you're going to do is you're going to have to install our ERDDAP. So, and then you're going to have to load that in. So our ERDDAP, it has been built to extract data directly from ERDDAP. So without you having to point and click. So there's a number of different servers that we kind of talked about some already where we provided direct links, but what our ERDDAP has is it already has a number of servers already located within it. So we have the Coastwatch West node, and there's your URL right there, and there's a ton that are already preloaded in here that are all federally regulated. So the University of Delaware one will not show up in this list, but you can use some of these if you wanted to. So we can search within our ERDDAP. We can search for different things like buoys. And now what we found is anything that has buoy in it. So we can actually search within here, and we say anything that has buoy data within here is going to return a link to a data set that actually has buoy data in it. So you can do things really quickly and easily within here. It's really cool with this query function. I mean, you can search different things and you can just really explore some data that would be a little bit more difficult and challenging with a raw Google search. So now what we're going to do is we're going to talk about how to get data that, let's say we have a specific data set that we want. Okay, so let's go back up here to where we had our printed servers out. And one of the servers that doesn't show up here, but that we actually want to deal with, is this NDBC data right here. So this is a named server that is within the server list. So what we will be able to do is, this is referenced, this CWWC NDBC MET is actually referenced to the National Data Buoy Center. And within that data, it actually has a direct link to the Upwell PFEG / ERDDAP. So this is our data set that we want to actually use here. So, and we just selected that, I selected that. It's just a nice data set to work with. And if you actually go to the Upwelling ERDDAP, you can view all 10,000 data sets. And what you'll actually find is, if we search for might be too big for it to show up, but this is a stored data set that can be referenced directly from our ERDDAP. So our ERDDAP has a link. If you type, this is the short name from it, and you can actually find a direct link to this. So that is what is going on here. So we print info out of that name. Our ERDDAP server already has a direct link to that URL, has variable associated with it. So we have latitude, longitude, time, wind speed, wave height, wind direction, etc. So we come back here. What we can do is we can grab info from those buoys right there, and we can select. So this is a ton of buoy data right here. What we can select is we can use THREDDS, which is a function from our ERDDAP, to grab the information from buoys info, which we stored right here. And we only are concerned with station, longitude, latitude, where we want the longitude to be -76, -74, latitude to be 38 and 40. So now we have location buoys, and these are all the buoys that are located with the station name that are located right here within our longitude, latitude bounding box. So now that we have that, let's say we are only concerned with buoys 1 through 4, so let's only parse that data, and we're going to convert as the longitude and latitude values to numerics instead of characters, or characters right now. And now what we can do, we can start parsing together a coast, and then we can use ggplot right here. To actually go ahead and view the data. So this is this is our data right here that from the buoys that we had. So these are just the locations of these buoys that were within our bounding box that we cared about. So just these buoys right here. So cool. We extracted all this information directly from ERDDAP, and once again, the only reason that it knew what this was because it already is linked together. So now let's say we wanted to do a search. We wanted to find SST that are within the ERDDAP search. So we ERDDAP search anything that has SST. So we print out which SST. So we have 1,000 different data sets that have SST data. Same thing if we wanted just MODIS SST. MODIS is a satellite. So about 170, 180 so MODIS sea surface temperature data sets, and here's the data set IDs. And let's just say that the data set that we actually wanted to use is called JPL MER SST 41. This is from the Coast Watch dataset. So here's our Coast Watch, and this is the data access form. So this is from the MER, which is a SST analysis model. It provides sea surface temperature. So this is our link right here. And it has a name, right here. So if we actually did which SST and anything that contained JPL MER SST 41, we can see all this right here. So we just happen to have this link in general, and the same thing can be said. You can use this function right here, ed search. So here we go. You have a query, you have a page, and you can actually do a more advanced search if you would like to really boil it down. But basically what we have here is we really wanted to use, we already have a data set, and that data set has a name, and it's located right here. So it can recognize that name with the info function from our ERDDAP. So it's from upwelling right here, space URL that it's going to grab. It has data from 2002 to 2021, longitude and latitude, SST, and that's what it is. It's just reanalysis of SST. So what we want to do is we want to grab data from this, right? So we're going to store the info behind that. We're going to store this as SST info, and we're going to use GridDAP to grab everything from the latitude 3045 and longitude -80, -70. Store that as last SST. So now, this is what it looks like. We have a nice table of time, latitudes, longitudes, and analyzed SST. So, and we just wanted the last time. So this is just all of the time right there. And actually what we can do is, now that we have this right here, we can just say, okay, my color equal colors temperature, and where does colors come from? Colors So this is a default colors that comes from our ERDDAP. So it makes things really nice. So we have this right here. We're just going to bring in a map data of world high res for the same location, and we're just going to use ggplot to plot it. Oh, I didn't run that. Now we can actually run it, and boom, there we go. Reanalysis of SST data for our specific box. So this is a really nice image of just some data right there, and we just grabbed it super easily. It's a little bit easier to grab using this than THREDDS. If you have an ERDDAP link to everything. And once again, we print out some random servers, and we can just grab any of these, right? And we can just say, okay, give me the info on emodnet. Oh, doesn't have that short name. So let's print out which buoys. And here we go. Then you need a dataset ID. So the dataset ID has to be the one that is used with info. And there we go. So as long as you have the dataset ID that you need, then you're good to go. And dataset ID for this one is JPL-MER SST41. So what happens if we have a custom URL, right? So we talked about these are preloaded things that we were able to search using this EdSearch tool with anything that contained a buoy in it, and that's how we found some of these different data sets. Well, what happens if we already have the University of Delaware data set that we want to interact with, but it is not located within the ERDDAP query search? So the way that we can do that is like so. So let's say we have a data set in this Marine ERDDAP right here. So this is just a Marine Institute ERDDAP, and we have Irish weather. And so we have this ID, IMI-NETL. So let's search that. So here we are. So this is the Northeast Atlantic model, and this is the dataset ID. So we have a URL to this ERDDAP, and then the dataset ID that has to be unique within this particular dataset. And now that we have that, what we can do is we can provide, we're going to give it this is our base URL. This is the parameter we want. And then down here under info, we say, hey, get this data ID, this dataset ID from this URL. And then we can plug in that specific info. As NA. And boom, there we go. So we have time, lat, lon, and sea surface temperature. We can turn this into, just print out a string of it if we wanted to, and then just like we plotted before, bring in world map data of just our xlim and ylim, use ggplot, and it's taking forever to plot, but basically the plot ends up looking like this. So, a lot to unpack there. Data extraction, there's just so much data out there that it's a little bit more ambiguous than just going into a datasets folder and extracting the one file that you need. So, for this assignment, just select any data set from a THREDDS server, create a script that loads in the data and plots it. In your script, explain why you chose the data set, detail each step, and describe why it's happening. Turn in the R script and the image plot you've made into UD Canvas. And then do the same thing with our ERDDAP. So just choose a different data set, choose a different latitude, longitude, and follow these steps in order to extract the data using these two methods right here. And then if you would like to, for extra credit, find a data set that uses TableDAP's instance instead of GridDAP, and use this method for storing point data instead of spatial data. Create a routine that downloads and extracts that data. But It's basically just find a data set of threads, find a data set of ERDDAP, and start downloading.